Alright, time for another DraftPhysics.com video presentation. Probably just more of me going over all these issues and subjects that haven't been touched by the opponents to my suggestion. Yes, that conventional physics has made some mistakes. So anyway, we'll start with the physicist Michael Guy. So there's no response, further statements made. Where the hell is that video? Random new. Where the hell did it go? Curious. I'll have to go looking for it. That should be it. Okay, so the thread where the physicist Michael Guy says yes, he's going to set up a thing and he's going to do his, he's going to do the experiment with a lever and prove that levers don't conserve momentum. That's his ambition, apparently. So it ought to be interesting. But since then, okay, things have gotten a little nastier. Anyway, so there's no response in text. I explained in text what exactly about his previous experiment where he used a spring to create motion. And in the two experiments, the same spring compression created completely divergent amounts of momentum. In one case, the spring produced twice as much momentum with more than twice the weights put on it. Somehow, it does that when springs are supposed to be conservative. They're supposed to conserve the force that pushes them. And so I pointed out that if you just repeat his experiment in reverse, you're not going to be able to compress the spring the same amount, which will show a huge inconsistency, that something's wrong. If the spring expands and produces one amount of energy, and then it takes a different amount of energy to compress it, it's kind of obvious there's a flaw. So will he concede the flaw? Will he fess up that the experiment ain't what it's supposed to be? Or will he just ignore the critique and, continue to propagandize for a theory that's not viable? All right. And so he has posted a new video that is just it's just so bad in the sense that this is exactly the same experiment he did here. So the work in kinetic energy, where there was substantial conversation, about the fact that he didn't really prove this kinetic energy exists, he just calculated it to exist. But this has exactly the same data in it, so he did exactly the same experiment all over again. It's exactly the same experiment. There's just nothing different about it. Except maybe the mass of the card, I don't know. The same stupid idea of let's drop a weight, and that somehow is a way of creating a consistent force. So I guess I should point that out first. So all of these points I'm going to make are going to be completely ignored because these people really just don't care. So he decided to post all this crap in the previous video about Ke equals 1/2, blah, blah, blah. Obviously they derived this, in a backward manner. They reverse engineer this formula and claim that it's F equals ma because they square acceleration for whatever dopey reason. And so you can see here PE, he's talking about potential energy, and he's claiming that the potential energy of this weight is going to be some sort of consistent amount that doesn't matter how fast or slow you move through the gravity, you're going to get the same amount of force, which is as dumb as their argument that it's the same work. No matter how slowly I lift a weight, I'm doing the same work. It's obviously a flaw in their reasoning and logic, and they won't just admit, yes, that doesn't make any sense. So, obviously something, the potential energy, if you want to calculate this as potential energy and you want to do it based on distance, you have to understand that that's the free fall rate. If you change the rate at which it falls, then you're going to change how much energy it's going to absorb or be affected by. So that's just sort of should be obvious to somebody that if it's moving through the gravity slower, it has an opportunity to collect more gravity. So its potential to collect energy is increased if you force it to stay in the gravity longer, just as if you lift the weight slowly, you're in the gravity, fighting the gravity longer, more gravity to fight. Now, that's a simple argument, and nothing from the objectors indicating how they're sure that it's a per foot force and not a per time force, even though it says 9.8 meters per second. So again, I could write that over and over. So anyway, you got the same numbers in these trials in the sense that the actual numbers are perfectly consistent with the expectation that twice the force is twice the velocity. And he perverts that through mathematics into saying there's 4 times the energy. there's no numbers that say it's 4 times the energy. I mean, there's no real variable that shows you 4 times. It's just their math that says it's 4 times. So in this video, he doesn't do any of that crap. So he doesn't apply any of the 1/2 mv squared stuff, and basically proves that momentum is force, just as Newton said. So when he wants to prove Newton right, he does this. When he wants to prove 1/2 mv squared, he does the same experiment and just does the different calculations. So it's just, so we're going to play this part of it and, where he's describing Newton's second law. And turn that up, turn this down. And somewhere in there it should be correct. So we'll see.
Is that the...
Okay, I'll turn this up. So this is his definition of Newton's second law. F, as they put it, F equals ma, which is not what Newton wrote or said in any way. So let's understand. Newton basically said you want to move something twice as fast, you apply twice the force. You want to go 3 times as fast, you apply 3 times the force. Basically saying the force is exactly equal to, the momentum. That force is momentum. Now the trick is, obviously, if you go in different directions, then those forces will cancel out in terms of the ultimate movement of the object. So if I accelerate this way and then I accelerate a little bit backwards, I'm going to have a net increase in one direction that won't be adding those numbers, it'll be subtracting them. So that's why I said proportionality. But in cases where you don't have any negative motion, you don't have to worry about any of that stuff, and it's just force equals the change in your velocity, because we're not changing the masses. And that's the simple truth.
rate of change of the momentum of a body is directly proportional to the...
So let's understand, it's only saying directly proportional because he has to account for the fact you can have more than one motion and they can subtract this from each other in the sense that the matter can do the math. There's no anti-force. There's just you did go right and then you did go left and then you did go right again. And those are real motions that are not in the same direction, and directions have to be canceled in the sense that they have to subtract.
Net force acting.
But that's directions. It's not motion itself. You're not saying the energy didn't exist. You're not saying it didn't go this way. You're just saying that it went more this way.
On it, and the direction of that change in momentum takes place in the direction of the net force.
So he said net force, and he's talking about if you add up multiple directions. And so in his subtext, where he describes what he said in that sentence, he makes it clear that you want to go twice as fast, you add twice the force. You want to go 3 times as fast, you add 3 times the force. Turning the proportionality into a direct equality. So he's basically saying force equals the change in your momentum. And if you want the net numbers, you have to use net numbers. You can't use ratios. You can't use rates. You have to use a net number. So if you want to know the net change in the velocity, you have to do the calculation and get your number. You have to get what the net change is, not one change and then add another change and then change, no. You have to get the net number if you're going to do the math honestly. So yeah, we'll play some of this just because it's dishonest math, frankly. First off, it's not what Newton wrote.
Let's talk about this one in a little bit more detail. Momentum is generally denoted by a lowercase p and is defined as the mass of the object times its velocity.
So he drew his little arrows, somehow indicating that real energy isn't in a direction, but momentum is, which doesn't make any sense. I mean, on its face, it doesn't make any sense, right? Their derivative, 1/2 mv squared, has mv right in the middle of it. How could something that has a direction lose its direction? I mean, it doesn't make any sense, again.
So this is a vector quantity. The direction of this momentum is the same as the direction of the velocity. And Newton's second law says that the net force...
So this is the lie, okay? That's not what Newton wrote. He wrote F. He didn't say F net. And then he provided you the opportunity to find it out in a rate, like 9.8 meters per 1 second. So if you want to know the rate of the force, that's different than the net force. So this is the first piece of a lie. This is not what Newton said. It's not what Newton wrote. It's not Newton's formula.
Acting on the object is equal to the change in the momentum.
That would be the net change, okay? It's not any change in the momentum. It's the overall change in directions. So you figure out the change in the directions of the momentum. That's what you're supposed to be calculating. And the net change in the direction is what you're supposed to have in that formula.
Over the change in time.
And there's no change in time. It's just you're using a unit of time to define a rate. So you can see it right there, right? I mean, this is a rate, 9.8 meters per 1 second. This is a rate. This is not a net force. So you can't do this. This is just cheating the mathematics. You can't know the net force by just knowing the rate. The rate would do you no good. You'd have to multiply the rate times how many seconds it happened. This is just telling you the rate per second, per any unit of time. The rate number will be dictated by what unit of time you use. You use the total time of the experiment. You could put that in here, okay, and you'll have a total change, and that would give you a net number. But those have to be totals.
Well, this momentum quantity is mass times velocity, and if we are assuming that we have a situation where the mass of the object isn't changing, the only way that this momentum will change under those conditions is if the velocity is changing.
Right, and Newton's statement on that is clear, so why don't you just say it? Newton clearly said there's a direct equality between force and velocity. Direct. F equals V. That's what he said. Those what his words exactly said. So why are you pretending we need this complicated formula when Newton basically said, look, if you're not changing the mass, it's force equals velocity. The change in your velocity. It's a direct equality. Response?
So I can rewrite this as the mass times the change in velocity over the change in time. And
so again, you still don't need this change in time. This is still a ratio. So if you're going to use this change in time thing, you have to use net velocity over the time, which really, the net velocity isn't going to care about whether you went this way or that way or this way. So time, you're not going to get a real ratio here. It's not going to work mathematically.
Your change in velocity divided by your change in time, how your velocity is changing with respect to time.
So again, it all starts with this force net. That's not what Newton was saying. So he was saying force rate equals the change in your momentum over the change in time. That's your rate. That's the 9.8 meters per second. Again, Newton's focus was talking about the force of gravity. So it was in this context that if you want to know the rate that the force is affecting you, this is what you do. But if you want to know the real net force, you don't need time. You just need the change in your momentum. The change in your momentum will be the change in your velocity, and the change in your velocity is exactly equal to the amount of force.
That is just what we call acceleration. So we can write this in the case where the mass is constant.
Right, so again, he's saying it again, net, and again, he's going to talk about acceleration. The net acceleration is the net change in your velocity. The net change in your velocity is the force.
We can say the net force is equal to the mass of the object times its acceleration.
So he's just replaced acceleration. So net acceleration is going to be the same thing as net change in your velocity. The two things can't be any different. So why did we bother with that? Oh, that's right. There's no reason to bother doing that. And obviously, if he was doing a kinetic argument, he would now change this into meters per second squared. He would just square the time for no good reason, merely because they say per second, which is useless. Mush.
It takes a net force to change the velocity of the object.
The net velocity. So again, it's just playing a game, right? The net force is the total impact. The total impact is now we've isolated to the total impact is going to be a total impact on your velocity. And Newton explicitly stated that the velocity change will be exactly equal to the force change. The application of the force will cause an exact change in the velocity. Same thing. Force is momentum. It's just in a different form, but it's momentum.
Cause that object to undergo some acceleration. The third law is...
Okay, so that's it, right? So he didn't do any of his 1/2 mv squared stuff or the acceleration, so he's totally taken kinetic energy out and stopped right there, which is kind of funny, right? So he does the experiment, blah, 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 and he still doesn't bring up kinetic energy much, I think. I mean, he puts a little square in somewhere, but basically the numbers come out to be the force doubles, the velocity doubles. The force doubles, the velocity doubles. Perfectly consistent with momentum as the theory governing force laws. All right. So I mean, it's just such double speak. You know, one video this proves kinetic energy. The other video it proves this perfectly symmetrical relationship between the application of a force and the change in your velocity. I mean, it's just, you know, what the hell is this crap? Yeah, it's just crap. Okay. All right, so just since we're on this subject of physicist Michael, we'll go over the thing he's evading, you know, the subject he's avoiding. You know, the one where he won't finish this, you know, comment thread. And I'll just draw that one more time, because there's not going to be, you know, they're not going to respond to the critique, the basic argument that you can't do what he's claimed he did. Okay, it's not possible, and he's claiming it's a credible experiment and that he can't be challenged on that experiment. Now this is, you know, I was going over the numbers. Well, I'll save that for the Brozo experiment, but it's just how your weight increases as you increase the velocity. And I had previously made an error in calculating that increase in weight, because you really do have to understand that the object itself weighs something. You know, the motion is one weight. The weight of gravity, the constant force of the weight, is also going to be measured by the scale. And you have to subtract that out to get right answers, which is sort of, you know, just, you know, there are details here, and everybody seems to be dismissing the fact that you have to scrutinize all this stuff kind of carefully, and they're all saying, no, you don't. Anyway, so the simple experiment was a spring, you know, one mass, Okay, and he got velocities, okay, and times the mass, and so we could just say momentum number was 100 going this way and 100 going this way. Did the same experiment with the same spring compression, so the same exact spring compression, all right, with two masses, all right, and got 200 and 200. So we have a total of explosive energy of 200 and 400. Same spring compression. So what's going on? I mean, what's the argument that somehow the spring can't release its energy proportionally, or it's, whatever it's trapped, and somehow it can give all kinds of numbers? I could just keep going higher and higher, and I can keep going lower and lower. By putting lighter and lighter things on, I'll get less and less energy. So again, it was just contrived to prove kinetic energy consistency. Somehow you conserve the kinetic energy, but it clearly isn't conserving momentum. It's nonsensical. So you could understand that obviously if I plow something with 200 momentums, p of 200, okay, and I plow something of p of 100, okay, that there's no way the spring would compress the same amount. So if I drop that on a scale, that weight, it's the same thing as saying I could drop a 5-pound weight and it would weigh 10 pounds. Or I could drop a 10-pound weight and it would weigh 5 pounds. Can't happen. So this contradiction can't exist in physics. It's just not really, it's not viable that this experiment is a real demonstration of real effects, because clearly this can't happen. This spring producing the wrong momentum. Now obviously I could put a bug in here or something. I could do something to fuck up the experiment so the numbers were wrong. But we're just saying, let's assume he calculates, he doesn't have some obvious flaw in the spring, like it has a broken bit in it or some other kind of flaw. There's just no way to account for this difference in the momentum. And there's certainly, again, if you reverse the experiment, the same energy should compress the spring the same amount. The release energy should be able to push the spring exactly the same as the release energy. And obviously these aren't going to weigh the same. This compression is going to be substantially greater, okay, than this compression. Twice as great factually. It's going to be twice the difference. So obviously if you can't reverse the experiment in the case of a conservational force, then that shows there's got to be something wrong in your experiment. So it's a perfectly valid critique of his experiment. It's simple enough and it's glaring. So speaking of that, glaring errors, we'll talk a little bit more about the Ian Gosling video. So let me go find that one. All right. So I guess I'll clean the board and just reiterate the point. I just noticed that in this comment section, let's see if you can see that. Nah, it's too far over. He has pinned this recent comment by this Michael Falwell moron. So this is after my video. This is this comment points out what I said in the video, and yet this is what they do. So instead of fessing up that he made an egregious error, I mean it's a big, giant, huge error in doing the experiment. Colossal, frankly. It's a colossal error. And instead of fessing up and claiming, yes, okay, I have to redo the experiment because I did it way wrong, he's doubling down. So I guess this will be something I'll go over again and over again and over again, like Brozo's 19 and 11. I'll have to just keep pointing out what lying scum these people are. Okay. And that's all they are, is liars. I mean, this is just nonsense. This experiment is so bad and so fucking flawed. So, he has notches on this bar that he put on ahead of time. And he's placed this weight below the notch. So the real falling distance is, this is more than 3 inches out of maybe a foot. So we're talking about a huge amount. 1/3 of the number is wrong. I mean, it's a 1/3 off, 33% off as a number. So the real falling height is this tiny distance here, right? This like 9 inches. Okay. And he's got these things marked at 12. So clearly the total height is way off. He's not going 4 times as high as this dropping distance. And then when he puts the lighter weight on, he puts it above the line, right? I didn't even see that before. But he puts it above, making it even more ludicrously stupid. So I'll illustrate it again, okay? Because that's what you have to do. You have to keep doing it over and over again, and they still ignore you, right? You can say for 2 years, please draw a lever and explain to me how it doesn't conserve momentum. Please show me in a drawing how the lever fails to conserve momentum. All right, so I am back. All right, so the idea of the experiment is simple enough. It's, everybody knows now. Galileo figured this out for everybody, a long time ago. 4 times the height. Okay, so you're dropping something, and you go 4 times the height, you get twice the velocity. Okay, that's what happens to an object because of gravity. Because gravity is really going to give you 1 unit of force here in this amount of time, and then it's going to give you a second unit in this amount of time. So you're only going to get 2 units of force. It's only going to take 2 units of time. And it will only weigh twice as much. That's what all this is about over here. And that's the truth. These are the true factual numbers. 2, 2, 2, and they say 4. Okay, they think gravity happens per foot. It obviously doesn't, or per meter if you want to be technical. Obviously it doesn't. Okay, it happens as time. It is like it's a rain, and it's how long are you in the rain is going to decide how much force affected you. All right, well anyway, so he's doing this experiment, and so he's taken a bar, and he's marked it with distances. Height distances, and he's made this simple error, okay, but it's obvious, simple and obvious. He's put the double mass, okay, which is 3 inches, all right, below the bar, below the mark. So the mark isn't calculating 4 times the distance now. He's got a number much bigger. This is the actual distance, okay, so it's like 9 inches. He's got 12 inches here, 12 inches here, 12 inches here. Obviously it should be 9, 9, and 9. So he should be adding, okay, a much lower number. So the height he's supposed to be dropping the half mass from. So it's a half mass versus a double mass. Obviously if momentum is a rational theory and Galilean mechanics are true, you can expect that because you're dropping it from 4 times the height and doubling its velocity, but you halved its mass, that it would have the same impact on the ground. It'll hit the ground with the same weight. Okay, and that's what we're looking for. Now he should have done this experiment already with a scale, and he was going to do it, and he pretended, okay, frankly, because he had already done it. And he found my prediction to be correct, and that's why he didn't do it. And so in this case, because he made this egregious error, and it really is egregious, right? So he put the half mass on top of the mark, okay? So he has the 2 mass below the mark, he has the half mass above the mark. So even that mistake alone would be pretty bad. But the fact that he got all of these numbers wrong, and he's not really dropping it from 4 times the height, he's dropping it from 5 times the height. If you add it all up, I mean 3, 3, 3, 6, 9, 12. You got 12 inches, you got a full increment of height off. Okay, so, it's a big, giant, huge mistake. And if you do the calculations, right, you get to 16 centimeters of height. You're talking about that 5-pound weight weighing 20 pounds. plus the weight of the object, right? So that's the problem. You always have to take the weight of the object out. Because everything weighs something on a spring no matter what. I can't remove something's real weight from what's going to happen. So if I drop from a height, I want to just know what the actual momentum is. I have to recognize I have to remove from that the actual weight of the object when I'm done. So if it weighs 40 pounds, it'll weigh 45, and I have to subtract the 5. But it's not a huge, in this case it works to his advantage, right? We minus 5 here, and we have to minus 10 from here. I mean, we minus 5 from over here, and we minus 2.5 from over here. All right. So, and to some extent, that works to his advantage, but he doesn't even. He's too stupid to figure that part out even. Anyway, but you know, this is a monstrous error. He's not doing 4 to 1. Clearly not. He's doing 5 to 1, frankly. And so he got numbers. So let's do the number part, because yes, I was wrong in how I stated the numbers. All right, so we got 74 centimeters and 60. All right, and he started with 100. Okay, so it's 100 millimeters of clay. So 74 would be 26. So we're saying 26 millimeters of clay were reduced. So you have that amount. And you're saying from their theory it should be twice that, okay, to be twice the energy which their theory says it has. All right, and so the 26 plus 26 would be 51, right? 52, sorry. So 52. Is it still on the screen? Not quite. Yeah, all right. So 52. Obviously, I'm saying they both have to compress the same amount, so they would both do 26. All right. So, so you just do the math for this is 40, right? So 40 would be 60 out of 100. Okay. And their number is 52. So they got 40 is what they got, and 52 is what they're supposed to have. 26 is what I say. And the number is 40, okay, which is 14 too much, as stated, 14. And this is 12. So we got a number that doesn't prove either theory. So just like Brozo, he's really just proving you can't do an experiment right. And it's certainly an insane exaggeration, well, it's a lie, to say proof of kinetic energy, yay. So why would you say that when your number isn't proof of kinetic energy? It's not the right answer for kinetic energy. Now, it's the wrong answer for momentum, but again, we know why it's the wrong answer. It's because you did the experiment wrong. And I will declare, I will predict, that if you do the experiment correctly, okay, you're going to get this 26 number. So go ahead and drop it from less high, okay, and put it below the marks or above the marks in both cases. Put the marks in the right location for where you're going to place the weight. And again, this is the dropping distance. The dropping distance was way short of the marks he placed on here. Way short. 30% short. Big shortage. 25% anyway. Giant cheat of the experiment. And like I said, this 40 is going to go way down when you take off this huge extra distance. Take away this extra distance, and this number is going to get closer and closer to this number. That's the prediction. Let's see if he has the integrity to admit his mistake, do the experiment correctly, and then change the title to proof that kinetic energy is wrong and momentum is right. Let's see if he has that integrity. So anyway, so I did the video last night. There hasn't been anyone acknowledging in all the 22 comments the fact that he did the experiment wrong. Okay. All right, so Falwell says, well, he did make a response to this, Ian, Yeah, you don't really need to read. No prizes for guessing that he spotted all the flaws. Well, they are real flaws. I mean, you can't tell that it's a flaw if you go above the line in one case and below the line in the other case. And then it's not a flaw that the distance isn't 4 times the dropping distance. The actual dropping distance. He didn't do 4 times the actual dropping distance. I mean, it's just, so I'm just saying this is showing their integrity. He's mocking these flaws as meaning nothing when they're catastrophic to the logic of the experiment. Okay, you can't pull the wool over his eyes that easy, So he's just mocking where there's a glaring error, a glaring cheat. So might as well call it a cheat now, right? Because they're basically saying this error doesn't mean anything. It's, this is just more blah, 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 blah. These are just words. It doesn't mean anything. Go ahead and cheat. That's all he's saying. He seems to struggle with the compression numbers as he did with the Mythbusters idols performed a similar experiment. Well, I was wrong to say it should be, in the previous video I said it should be half of 74. Well, yeah, that was wrong. That was 37. So, there's not a huge difference between 37 and 40, but whatever. It's a difference. So let's use both models as a measure of energy, P versus KE product and predict an outcome. The same in both cases. So he's just ignoring that clearly it wasn't 4 times the height. Clearly it wasn't. It was much higher than 4 times the height. Significantly higher. 20%. So this instance we should predict roughly equal amounts of compression in both examples. Yes, that would be the rational prediction, and it is in fact what took place if he had dropped them from the right distances, which he clearly didn't do. Okay, he predicts 2x the energy, and we should see the compression something less than 2x. I don't know why it's less than 2x. That's an interesting cop-out of some kind. As the more you compress the material, the more energy it takes to compress it. So that's completely illogical, that somehow the clay is harder to compress. I mean, there's absolutely zero evidence of that in any experiment. Okay, real world results. 2 mass at 1 velocity. Pre-compression 100. So we have total compression 26. And so he says total compression 40. I mean, obviously, those numbers don't match. 56 is not 40. Yeah, it's not 40. Okay. So if we use P and P alone, it's more than evident that the real results don't match the prediction. So again, totally ignoring my overt claim that it's not 4 times the height. It's much more than 4 times the height, the dropping distance. I mean, fuck. That's just how they're just such liars. So he pinned this piece of shit comment. So he says somehow 1.54 is 2. 1.54 is 2. Yeah, no, it isn't. Oh, so he says, brilliant, Mike. I'm going to do more of this. Oh, the wrong way? You're just going to keep doing it wrong? Oh, P.S. To be clear, there was no intent on my behalf to pull the wool over anyone's eyes, or never would be. Thanks, Mike. Well, you're pulling it right now. You're not conceding the experiment was an absolute pile of shit. You didn't drop the weight from 4 times the height. It's just a fact, an absolute fucking fact. And then you didn't even get it right in the sense that you put one weight above the line, you put the other weight below the line. I mean, it's an absolute steaming piece of shit. Jeez. All right, so somebody says the end is nigh. Yeah, I think that's just recognizing that, what the fuck? He didn't do the spring experiment because my prediction was the truth and accurate. And so he just keeps doing it. Oh yeah, it's very exciting times. I'm going to improve this demo. I mean, what? and help usher in the truth. Keep watching. So look, if anybody has a little tiny bit of logic, they could recognize that he's just proven me right. Because we know that 40 number is going to get damn close to the 26 number, okay, if he takes away that extra height. So he drops it from a lower position. We know it's going to get closer and closer and closer. Oh, he's such a liar. Alright, so we'll read some of this crap, but whatever. I mean, these were comments before my video. Well, I don't know about this one. At least we don't live in our niece's basement. Shameful. So again, what is this? I mean, he continues to lie about my personal life in comments. Now, why would somebody do that? Why would somebody worry about how I live and what my personal living circumstances are? Why would that be relevant in any kind of conversation between anything called a rational human? And he's just wrong. I mean, I have barely even met my nieces, frankly. Okay, I saw them when they were little kids. Okay, that's all the only contact I've ever had with them. So what are you talking about? Great experiment, Ians. Keep it up. I mean, you're just such an evil. I mean, it's just so evil to have to deal with this. Why should I have to do this? Why should you allow commenters on your videos to invade another person's personal life like this? It's a physics argument. I mean, really, Ian, should I look you up? I mean, should I, try to Google you and see if I can find out what you're married to or how you live and all that kind of crap? And then if I can find out any information, I should make it public? I mean, that's our job here, fucker. Oh, amazing. Amazing that this is what they have to resort to. They can't draw a fucking lever and instead want to draw a picture of my life when they know nothing about it, frankly. Even though most of it was public. Anyway, make a video explaining how the lever works instead of making these crap experiments. Well, this one was real crap. Let's see what he says. How about a please? Manners cost nothing, pit dweller. So, that makes a lot of sense. Yes, we just called him coward, which he is. And now I just don't see how he recovers from this, frankly. I mean, he's proved a grotesque incompetence. He's already evaded doing this experiment in one circumstance with the scale because he knew I was right. And then he does it wrong with the clay. And will he have the integrity to admit that, well, if I'm going to say this wrong experiment proved kinetic energy right, and I do the right experiment and proves momentum right, will I say the argument's over? Will he have the integrity to say, oh, yeah, I guess the argument's over because I declared it over on wrong information, so I guess if I do it the right way and it comes out his way, then I guess he has to concede the argument and be done with this. I mean, just amazing. Alright, so this is the Falwell asshole previous to my video. I was going to say, where was your quick release? Well, why didn't you ask him, why can't you measure right, you moron? But a disciple beat me to it. Great demo, Ian. So again, just huge flaw, glaring flaw. And they just couldn't care less. Okay, the bit him and his followers can't seem to grasp is that having a mass alone with the same applied energy, so we know it's not the same applied energy in the sense that it's half the mass and gravity affects things based on their mass. It gives heavy things more energy than it gives light things. As a double mass doesn't make it go twice as fast. So I don't even know why you would say as a double mass doesn't make it go twice as fast. I don't even know why you'd say that. It's obviously a half mass, but regardless, we know it falls at the same speed. If you want half the mass to go twice the speed, you have to add more energy. So there's absolutely no evidence of that, for that to happen, which is clearly demonstrated here by your good self-mate. So again, applauding a completely shitty, flawed, corrupt experiment. Designed and promoted for the mere purpose of proving me wrong, Okay, not for doing good science, not for the purpose of defending their own science, just for the purpose of proving me wrong. Okay, and he's exonerated me completely, which is the joke. Just for clarity, Mike, I believe the half mass does in fact achieve double the velocity. So now Gosling is correcting the moron, resulting in more energy and a greater compression of the clay than their MV would predict. So it doesn't even make any sense. It's double the velocity. It's not triple the velocity. Double the velocity is double the weight, is double the momentum. Point is, according to him, there would be the same result if you had dropped it from the right height. There would have been. Okay, if I had a quick release and pink socks, of course. So, haha, laughing. So he makes a Joe, you can't even describe how it's a monstrous error. In your example, the half mass traveling twice the speed of the full mass, they both have the same momentum. So his logic is they possess the same amount of energy. Duh. Our ability to do work in the universe, as he likes to say. Yes, exactly. It's 1,000 atoms going 1 mile an hour versus one atom going 1,000 miles an hour. It's the same currency. 1,000 pennies is the same as $1,000 bill. But to make the half mass achieve 2x the speed, you have the same momentum. You had to add more energy. So he keeps saying you had to add more energy. There's no source of more energy. You have the mass and double the velocity. There's no more energy. To the half mass than the full mass. It shows that momentum and energy are not the same thing, blah, blah, blah. And E equals E, whatever, I don't know. Why would even somebody write E equals E? You get back what you put in. Again, doesn't make any sense. And your demonstration illustrates it perfectly. So he's saying 4 times the distance in gravity means 4 times the force. So he still he won't concede that it's a time-dependent force. So even though it says 9.8 meters per 1 second, even though that's the exact statement, he's pretending, okay, that time doesn't matter. So he's pretending that it's the same work. No matter how slowly I move a weight, I'm doing the same work. And your demonstration illustrates this perfect, hence different amounts of compression. So obviously the illustration was, what's the right word? I mean, it's flawed, doesn't even explain how bad the experiment was. Alright, thumbs down this time, boy. You better watch again. Clearly shows me measuring the length ready. Let's see, what is this? So I don't see this original comment by this guy. Thumbs down this time, boy. You better watch again. Clearly shows me measuring the length ready for the second drop, for your dishonesty is only surpassed by your leader. So his video is completely flawed. He knows it. And he pins a comment that ignores it. Ignores the flaw entirely. Doesn't pay any attention to the egregious flaw. Alright. So now they're just talking about how big the clay is. Now I'd say the bigger issue is that he heated the clay. So yeah, I'm not going to get into this minutia about bullshit. Let's see, so these are all 17 hours ago, so this is all before my video, so we can probably ignore this thread unless there's something being it's all before my video. Alright, let's see if there's anything else these 19 and 20 hours ago, so it's probably not worth the trouble. Let's see if he said anything in response. Nope. Alright. Okay, so so I guess we'll just do the number thing. So everything is a little, in all of these conversations, there's lots of stuff to be aware of. It's not as simple as they want to make it, and in some cases, I could have been guilty of the same thing. All of it's a little bit, complicated. All right, so the simple argument is that you're gonna drop something on a scale and measure its weight. Okay. The fact is that this moving part is different from the fact that this always weighs. So if this weighs 10 pounds, it always weighs 10 pounds. So if I'm going to drop it, the fact is it's already going to weigh 10 pounds. I can't get rid of that. It has to push the scale 10 pounds just because it weighs 10 pounds. And now I'm going to drop it, okay, then I'm going to be adding a new amount of weight. So the fact is I drop from 1 centimeter, this is how it works out, okay, I'll double its weight. But the only part that comes from dropping it is this portion, right? This portion is the 10 you automatically get, you can never get rid of. So this is really the dropping addition. With the dropping motion, the momentum of the drop is only 10. It's not the 20 you see on the scale. So the scale is saying 20, the instantaneous weight. But the only part that came from dropping is 10 of it. All right. So that's what creates some confusion, because you have to extract that to know. And so now when you're saying you're going to drop it from 4 times the distance, okay, so you did 1 centimeter, you're going to go 4 times higher to 4 centimeters. Now what's the expectation? Which one are you doubling? Are you doubling the 20, or are you just doubling the 10? And so my point is you're only doubling this 10. Okay, this is the only portion you're doubling, is this momentum portion. All right, you're not doubling the 20. But yes, when you get your reading, you have to subtract 10 from that reading. So you always have to remember to subtract the 10 out of whatever the scale reads. So you'll compress it 10, but it's going to read, okay, a different number. All right, so when you go 4 times higher, it's going to be 20. All right, so you're doubling the 20. Okay, so I have the numbers over here. You really can't see them very well, but okay, so 1 centimeter is 1 mile an hour. Okay, so that's what it gets you. So you drop from 1 centimeter, it creates a velocity of 1 mile an hour, and it will give you your weight. But the scale is going to read 20, and the actual momentum is only 10. So if I go 4 times higher, I'll get 2 miles per hour. All right, and what I'm going to be doubling is the velocity, which is the portion of the momentum, which means I'm only doubling the 10. So I only have 20. Okay. And then when it's 4, okay, then I'm going to be doubling 4 miles per hour. All right, doubled the speed. It's going to be 40. All right. So that's what you have to do it by. So it's 1 centimeter, and then it's 4 centimeters, and then it's 16 centimeters, and so on and so on. And so you can understand in his experiment, we're talking about maybe 15, 20 centimeters worth of change, which in his case would be 20 or 30 pounds of extra weight, 5-pound weight. In this case, 2.5 pounds, but whatever. It's substantial amount of extra weight that never hit the clay. That would have never hit the clay if he did the numbers right. He obviously created a bunch of extra weight in the 2.5 mass object, so clearly the experiment is way off to my benefit, completely to my benefit. All right. So in the clay experiment, we can't extract the weight of the object, so that was sort of my point. But the good news is it becomes insignificant. So if the amount of the total weight from dropping 4 times the height, if the total weight of the 2.5 ends up being 25 pounds, well, then you can understand that subtracting 2.5 from 20 pounds isn't going to make that much of a difference. But anyway, there will be a little bit of difference, because in one case you're subtracting 5 pounds, and in the other case you're going to subtract 2.5 pounds. So how much 2.5 compresses the clay is what you sort of have to measure. Is it 2 millimeters, 1 millimeter? But yes, that has to be subtracted out. The standing static weight of the object has to be subtracted out of the numbers. Now you can do that well, you can only do it by subtracting it, right? So by knowing how much it actually deflects the clay. But anyway, you can do it by just recognizing the percentage is small, and it won't make much difference in the numbers. But you would argue that the 10 mass has a slight advantage. So let's say the 10 mass appears to be a little heavier, okay? I mean the 5 mass in his case. So he drops the heavy weight from the shorter. Let's say he does the numbers correctly the next time. You would predict that the amount of compression of the clay is slightly going to be to the heavy mass's advantage, in the sense that the number is going to include the weight of the 5 versus the 2.5. You're going to be subtracting a bigger number from the compression. But anyway, it's not nearly as big an issue as the gigantic issue of him measuring completely wrong. So just show that as the last thing and get out of here. The measurement is completely wrong. This dropping distance does not equal this distance that he's marked. So it's way off. These notches are all 3 inches too long. 3 inches, 3 inches plus 3 inches. So it's at least anywhere from 9 to 12 inches inaccurate in terms of the dropping heights. And he won't, so far, he's seen my video and he won't concede the point. So we'll see where that goes. I mean, it's just showing that he has absolutely zero integrity. He's, talking about how he's going to do more experiments the wrong way. Yeah, amazing. But not unexpected. Like I said, for 2 years I've asked one of these morons, please, I could ask the question, how much do I have to pay you to draw a lever and explain how it doesn't conserve momentum? Explain what magical thing stops it from conserving the momentum. Alright, so enough said, I think. See where it goes.